Good morning, folks. I hope you can hear me well since I'm at the airport now. My name is Konstantin Grotov. I'm from ITMO University, and I'm very happy to be the first presenter at the AINL conference this year. I will present my work made with Valentin Malych on step-level uncertainty estimation for LLM agents. In short, it's the study on how we can predict whether the agent's code will crash before it runs, using only the model's own log probabilities and the history of what happened so far. So nowadays, large language models agents are no longer just chatbots. They're deployed in various different applications, different multi-step workflows, such as scientific data analysis, financial modeling, automated long horizon code generation, and many, many more. In these settings, the reliability of our agents matters as much and even more than its accuracy. A system that produces a plausible but incorrect analysis and expressing simultaneously high confidence can be more harmful and dangerous than the one that correctly understands its own limitations and communicates its own uncertainty. And recent surveys in recent years show that the rapid use of agentic systems in production and growing need for reliable uncertainty estimation. So what do we need? Confidence calibration is that we want the predicted probability match with empirical success rate. A well-calibrated agents or additionally calibration models will allow us building actionable systems such as routing to low confidence outputs for like additional human review, or triggering execution of uncertain steps with bigger, more capable models, or completely stopping early when like the reliability is already very low. And as a result, it would help us save significant resources and money in the end. However, the challenge is that modern large language models tend to be overconfident. They express high token level probability in many situations where they either like completely wrong or lack needed knowledge to solve the particular task. There are already many studies which establish the calibration for neural networks in general, and recent work confirms that such methods can transfer quite well to the even frontier large language models. However, calibrating agentic systems is completely another beast, and it's harder than calibrating models operating in single turn setup because of two challenges which are very specific to agentic systems. The first challenge is compounding uncertainty, or it's simply the fact that errors and misconceptions in models accumulate across the trajectory. For instance, an incorrect data transformation in the earlier steps, it can silently corrupt all the downstream results which models can propose. And the agent can still may continue expressing high confidence through the further trajectory. Secondly, it's heterogeneous signals in the trajectory. Agents interact with various external tools, for example, programming interpreters, and the responses, like such environment observations, they induce different uncertainty behavior, since by nature they are out of distribution for our main large language model. And even synthetically confident function call can fail because of unexpected data properties where work in real environments, and everything can go wrong there. The pattern of success and failures across the trajectory carries information that raw log probabilities alone cannot capture. So prior agentic-specific calibration studies mainly targeted the trajectory level. So we are given a complete multi-step interaction and finally predict whether the final output is correct. So is the task solved correctly? This is very important, useful task, but in the case where we have a weak, in this case, we have very weak causal connection between the single step log props and our final answer. And in our work, we take a step back and ask a more targeted question. So can the model predict from its own token level log probabilities, which are accumulated to like the current step, whether the code it just wrote will execute without error? This step level target is better posed in several ways. First of all, we have verifiable ground truth. So did the code actually crashed or not? Secondly, the signal is produced at the exact moment of interest, and like practically we get roughly 10 times more labeled data per model. This also lets us measure how much of uncertainty information in code is at the local level. So here is the formalism we used in the study. We have an agentic trajectory. It consists of a task query and then a sequence of actions, observation, execution labels, and token log probabilities. Our objective is to learn a calibration function f that maps a feature vector extracted from the log probability and the execution history, and then repredict a probability in range from 0 to 1 that the current step will succeed. We use regularized logistic regression as the calibrator. It's enormously simple, interpretable, and like efficient method which widely used in prior works. Yeah, here is the example of agentic trajectory. So again, we have a task, then we have multi-turn of tasks, action, and observation loop, where the agent explores the environment and solves the task step by step, and then it proposes the answer. We can derive the log probabilities from the generations, and we can get the success labels from the observations. Then, in our study, we construct a vector of features containing the signal features and history features and train the model based on it. So, as was already mentioned, our feature vector has two layers. So the layer 1 contains 48 signal features. This is the full holistic trajectory calibration feature framework vector from Zhang et al. Work, recently published, and computed causally on the prefix up to the current step we're like exploring. It captures 4 groups of different features like dynamics, position, stability, and structure. And the second layer contains 20 additional history features, which are capturing the pattern of preceding tool call outcomes. This includes global statistics like success rate, positional features like previous outcomes, and failure geometry features like maximum consecutive failures. Critically here that this layer of features requires no access to log probabilities. So it would work with any black box API without log prob access. In our study, we evaluate 3 configurations of models of like feature vector, the full model with all of the features, the no tool model without tool related features, and tool only with like tool features only. And we evaluate our methods on DA code. It's a complex benchmark of 500 data analysis tasks requiring multi-step code execution, looking into the data, and solving tasks formulated in natural language. And we ran 2 models, Ministral and Quentry-Coder, which are from different families, and extracted all steps with available token log probabilities to perform further training and analysis. A key observation in the data we have to keep in mind that the step success rate is dramatically higher than the task success rate. This means that agents fail at the task level far more often than like at the individual step level of individual tool calls. And in total, we had more than 9,000 of labeled steps. Let's move to the results. In the table, we show the comparison between different models and different feature vectors we have trained. The calibrated models based on different vector features. Okay, so doesn't matter. Here, we will focus mostly on our rock column, which showed the discriminative power of our models. And the trained full model achieves best ROC score both for ministerial and Quantum Recorder model compared to the both task level results and for baselines. Yeah, the shaded rows at the bottom show the task level references for comparison. The trained model significantly surpassed baseline's values for the step level, indicating that the log props actually carrying a lot of valuable signal for accurate prediction of tool execution success. And interestingly, that step model only, which uses only execution history with no access to log probabilities, once again, achieves quite competitive score, which is worse, yes, but it's already above the baselines and more than task level results as well. So simply tracking whether previous steps crashed is quite informative. Regarding reliability diagrams, before calibration, temperature scaling baseline produces prediction that clusters near the mean. So it's formally acceptable calibration with quite good expected calibration score metric, but useless for actual decision making. And after the calibration, like after training our full model, the bars closely track the diagonal line. And the metric even drops down and predictions spread meaningfully across the confidence range, which enables like both the great calibration and high ROC discrimination score we're looking to. And we also looked at which features matter the most. In full model, no single feature group dominates. Like the top predictors come from dynamics, position, stability all simultaneously. And it confirms that the holistic trajectory calibration taxonomy proposed in original paper actually captures complementary aspects of uncertainty, not only the benchmark they proposed, but on others as well. And tool history features, despite their competitive standalone performance, rank below signal features in the combined model. And in the tool-only model, there is a clear asymmetry. So we have the fact that failure indicating features carry larger coefficients and carry more signal than success indicating ones. And this is consistent with the observation that failed steps can corrupt environment state, like partially write files incorrectly, drop columns in the data, and others failures. And this tends to propagate forward in the agentic trajectory. So failure autocorrelation is a consistent structural property of our agentic trajectories. So two trajectories can have similar aggregate success rates, but in the end, opposite outcomes. So one that fails early can recover later, has positive gradient of success over the steps, and in the end can produce task success. On the other hand, the run which runs smoothly and then breaks down in the end got negative gradient and task failure. So our gradient, our dynamics features capture this distinction quite well. So given the high base rate of step success, observing a failure is substantially more informative than observing another success in the trajectory. So to summarize, here are three findings. So first of all, log prop signals are informative for local code execution, even on more complex benchmarks for agentic confidence calibration. Secondly, agents are far better at local than global self-assessment based on such features. And third, that tool call history provides complementary signal without log prop access, and these features alone are quite competitive, which opens new direction for developing such methods for practical monitoring of black box APIs, LLMs. And this work has several further research directions based on limitations. First, our current features are derived entirely from token level logics, and problem hidden states could provide like richer uncertainty signals and more flexibility on how we can train those models based on the model's internal representation. Secondly, our 20-dimensional history encoding could be done definitely better, and now it's relatively coarse. So incorporating different error types, longer temporal context, like tool usage statistics, could improve the tool on the baseline significantly. And the third, we evaluated only on one benchmark with one simple agentic scaffold. So it would be very important and interesting to test it out on other benchmarks and prove, like to show is it generalizes or not. So this is it from my side. Thank you very much for the attention. Our code and data are publicly available, and I will be very happy to answer all of your questions. Thanks.
Thank you. Thank you, Konstantin. Do we have questions from the audience? While people are thinking, actually, I'm a co-author of this paper, so it's really not me who should be asking, but maybe you could describe in a bit more details how you could apply some, of course, not this exact method, but some analog method to the black box scenarios. It seems to be that you need white box access.
Yeah, so thank you for the question. So I will return to this slide. So in our approach, when we're working with open source LLMs, we have much more access. We have both access to log probabilities, like to hidden states, and like we can do with trajectory everything we want. In black box LLMs, like when we're working with API, we have only the trajectory. So the idea is that we can just remove all the signal features. So it's the same as tool-only approach, which I described like in this talk. And it still would give us some meaningful results. So it still carries enough signal for at least some discriminative power. In our case, this history features was like very simple. So we just looked at the success labels of like what code crashed or not. We don't need to have access for log probabilities to have such data, but we can even like further encode more information based on the trajectory. It could be not only information regarding the tool calls and tool observations, but also some like general statistics on the trajectory, like the thinking tokens amount, how it changes over the trajectory, and so on.
Okay. So as far as I understand, you were saying that we can just keep some features and still get some results. Maybe not really forced.
Yeah.
Okay. Thank you.